Gee, well, we've gone into a fifth lecture. Sorry about that. This will be real short, but I did want to conclude with an example and remind you that, and this example is similar to something you'll see on the little 5-point extra homework problem that I'll post along with these notes. So that's why I thought it'd be useful to show a couple of examples. All right, so for example, oops, switch back to black ink here. Now, suppose that we want to sample speech. We're going to have some audio, like cell phone application, and the bandwidth is, we happen to know, is 3.4 kilohertz. Okay, what should we use for the sample rate? Okay, and the answer is, we can first calculate the Nyquist sampling rate, which is 2b, 2 times the bandwidth, which is 6.8 kilohertz. Now we always sample higher than that, right? So we always sample above that, and I recommend 10 to 20% above that. We can just choose, in a test question or something, just say, well, I'm going to choose like 10% above that or 20% above that. So you might just write Fs is equal to 1.1 times 6.8, which is 7.5 kilohertz. Okay, when this is the problem that the phone company faces, whether your cell phone company or whatever, they actually do a sample rate of 8 kilohertz. And sometimes sample rate is just posed as in terms of sample rate in kilohertz instead of kilosamples per second. But everybody knows what that means. Okay, well, there's one final idea I wanted to give to you, because I think there's going to be a little question about it on the homework, and that is that how does a low-pass filter work in the time domain? We've got this kind of a sampled signal, and I'm saying that if we low-pass filter this thing, remember this is just a terrible sequence of delta function impulses, and if you listen to it, it would be like pop, 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 but it would be real fast pops, and you could actually hear the original signal in there, but there'd be whole lot of high frequency noise. Well, if we run this through a low-pass filter, a low-pass filter is just a smoothing filter. They call it a smoothing filter. It removes sharp edges. What it does is it actually kind of connects the dots. So we've got these samples, and the low-pass filter fills in instead of the original signal, which is kind of zero in between these things. The low-pass filter is going to connect the dots. But it does so in a very optimal fashion. It connecting the dots, if you remember, is called interpolation. When we don't know what's between two known values, we can interpolate and make a guess. This is ideal interpolation. What that means is, remember, we don't get just any old estimate of x of t. We get x of t. This is exact. So using an ideal low-pass filter, we exactly recreate this information between samples, so which is actually kind of miraculous if you think about it. We never measured those, and yet we can fill in the gaps exactly. All right. So exact reconstruction. This is also, so this is called ideal interpolation. This low-pass filter is the ideal interpolation filter. And just remember, it's only possible as long as we choose the sample rate to be greater than 2 times f max. If not, there's nothing to if we didn't honor that, the kind of thing that would happen is we could have a signal that maybe did all kinds of crazy stuff in between these samples. Okay, this kind of a signal would not satisfy the Nyquist criterion, right? Because it has all kinds of variation between samples that there's no way we could guess. We couldn't interpolate and recreate all of this variation between samples. So what we can do is recreate exactly low frequency variation. So as long as we honor the Nyquist rate and sample at that rate, we can get exact reconstruction with an ideal interpolator, which we call a low pass filter. So that's the end of that. Sorry to go to 3 lectures. Make sure you check the little homework thing that's attached to the notes that are posted.